Lesson 6 in Unit 1 is limits and continuity. I've hinted at it, I've talked about it, but this is where we really get to talk about the definition of continuity. I feel like you already know all the pieces, but it's just play it all together. So we have an understanding of limits and using limit notation. Now we can use limits to define continuity at a point. This is a huge thing, is to be able to talk about, is a function continuous? In lots of our theorems and various pieces that we do throughout calculus, you have to be able to know, is something continuous? And that's what we're going to talk about. So, important concept here. Now, example 1 calls it a discovery explanation. We're going to use the graph to complete the table below. And then, as we get this, there's going to be 3 conditions that are necessary for the definition of continuity. And we're going to talk about what those 3 conditions must exist in order for f of x to be continuous at a point, x equals c. Now, let's start off by filling in the first column. Okay? So, these are just find the function value if it exists for a given x value. So, using this chart here, when x equals 9, what is the value of the function? What are you going to estimate that to be? 3.5 sounds good to me. Okay. When x equals 4. D&E does not exist. Or you'll often hear undefined. Okay, so D&E is what she was using to fill in, but undefined is a common vocabulary there because there's just no values. Okay, when x equals 3, 9. There's actually a point there, which is weird because usually I'm used to seeing an arrow going up alongside an asymptote. When x equals 0, 6. When x equals negative 3. Did you guys catch that? Negative 6. Don't go for the open hole, go for the point, yes? And when x equals negative 5. Again, if you're going for the filled in point, negative 2, correct? So that's just the function value. Okay? Now we're going to repeat. This time it's the left-hand limit. So as x approaches that value from the left. So as x approaches 9 from the left, where are we going to approach? As x approaches 9, so as we approach that point, what is that point that we're approaching? Y value of 3.5 still. Again, if it was an arrow, we might be going more for 3, but. What about as x approaches 4 from the left? I'll be honest, I hadn't seen this exactly done this way. Okay. As we approach 4 from the left, does my graph approach 4 fully? It stops at 3, doesn't it? Does it ever approach 4? No. So we're going to say D&E. Because the graph doesn't go past 3, so the graph is never approaching 4 from the left. As x approaches 3 from the left, there's your 9, yes. As x approaches 0 from the left, there's the 6, bless you. As x approaches negative 3 from the left, 5. This time it's the limit, so as the graph is approaching there, you are moving towards an empty hole, but that's fine. And as x approaches negative 5 from the left, negative 2. Okay. Repeat as x approaches from the right. And you're going to stop me if you're not okay with one of these answers, right? Okay. As x approaches 9 from the right. There's nothing over there, so this is a D&E. You can't approach 9 from the right when the graph is not leading us towards 9. Okay? There's nothing leading me towards 9. As x approaches 4 from the right. There is an arrow this time, so we're going up to infinity. As x approaches 3 from the right. D and E. Because we know it approaches 4, but it doesn't go past 4, so there's just kind of a gap there. As x approaches 0 from the right. 6. As x approaches -3 from the right. 5. And as x approaches -5 from the right. We're up top now, 7. Now, for this next piece, we don't have to look at the graph. We can look at the chart. The general limit. So when we talk about general limit, this is as x approaches from the left and from the right. So as x approaches 9, what do we know? It's 2 different answers, so do we have a limit as x approaches 9? We do not, because it approaches 9 from the left, but it doesn't from the right. So that does not exist. The limit as x approaches 4? Again, one side it doesn't exist, the other side is going to infinity, so it just does not exist. The limit as x approaches 3. One side 9, the other side does not exist, does not exist. Okay, what about the limit as x approaches 0? We get a number answer, finally, 6. 6 from the left, 6 from the right, so the limit is 6. Limit as x approaches -3. 5 from the left, 5 from the right, so 5. Does it matter that the x value had a different assigned y value? Does not. And the limit as x approaches -5. Yeah, -2 and 7 are not the same again, so it does not exist. If you look at the graph, does the graph give you those same answers? Yeah, it was just quicker since we already had them filled in on the chart. Now, okay, continuity. Is f of x continuous at x equals c? Would you say yes for any of these? What have I kind of talked about? If it is continuous at this point, whichever point we're talking about, the limit from the left has to equal the limit from the right, and the value has to exist at that point. So it has to equal the value at that point. Okay, when x equals 0, what did we notice? It's 6, 6, 6, all the way every time, yes? So, at x equals 0, yes, there is continuity at x equals 0. What about most of the rest of these? Now, there's one special case, but most of them are no's, aren't they? The one special case, and I think this is just because it's the end of the graph, maybe, but at x equals 9. And you don't hear this talk very often, but she said it is continuous on one side. And I think that comes into the graph ends here, so maybe that's why she's willing to say that. As I said, I'm not, usually you just talk about continuity. The left to the right, and they equal the value that connects them. Okay? But she talked about that, yes, this is continuous at 9, but one-sided only. So it's only continuous from the left. Okay, so I will go ahead and mention that. Not what you usually, not what I want us to focus on, though. Okay? The others are all no's. Okay? All the rest of those, if you look at the graphs, as we approach 4, no, because we have a stopping point on the left. As we approach 3, no, because it doesn't come from the right. As we approach 0, Well, that one was a yes. As we approach -3, that one's a no only because this value is removed, right? It's a removable hole. And then -5, you got two different limits going on. Okay, so definition of continuity here. Let's fill in our pieces. First thing I'm going to list, I'm going to use the official talk. F of C is defined. You understand what I'm saying there? There's a point there. It's not a hole. The value does exist. Okay? So the value does exist. It's not a hole. That would be what I'm trying to say there. Okay? The limit as x approaches c of f of x must exist. What do we mean there? Yeah, this is the way of saying the limit from the left and the limit from the right must be equal. And again, you know, there's part of me that feels like the limit as x approaches c from the left needs to equal the limit as x approaches c from the right. Okay? And I'm just going to say up here, value exists. No hole. Now, the third one is just putting these together. That sounded really weird. The limit as x approaches c of f of x equals f of c. So that is saying the limit, so the limit from the left, limit from the right, so the limit equals the point. F of c representing the point, right? Does that make sense? This is the kind of the fancy lingo, isn't it? But you've got to understand what it means when you read it. Sorry, I looked at the clock and I had a brief moment of this is 5th hour and we get out sooner rather than later. No, sorry, not. Okay, got what you need? Okay, the next page. While limits told us where a function intended to go, continuity guarantees that the function actually makes it there. Okay? So while limits told us where a function intended to go, continuity guarantees the function actually made it there. So continuity is putting it all together. We've talked about these discontinuities here, right? None of these are new to you at this point. You've talked about them. We're going to talk about them some more today. We have what we called holes in pre-calc, right? We've talked about them as holes. They are removable or also referred to as point discontinuities. And on these holes, the limit exists on both sides. There's a limit that does exist there, isn't there? Because there's two-sided. On a side note, one thing I want to mention here, this could also, if the point, you know, there's this hole right here, but if the point exists somewhere else, that also falls into this category. So just kind of as an example there that this could have the point defined elsewhere, which is what I was trying to show by drawing a point there. Okay, it wouldn't have to. It works either way, whether it's a hole or what I call a removed hole when just the piece is elsewhere. So, okay, jump continuity. These happen with piecewise functions. Okay, the limit only exists from one side or the other. It's never the same on both, but there's a jump. And again, you won't see this in a regular function usually. It's usually piecewise. Only other place I can think of this is there's an absolute value function that we've seen a couple of times, and I'll point out either later today or in homework. And then infinite. These are what, when we usually find vertical asymptotes, right? Vertical asymptotes are your infinite, also fall into the non-removable, okay? At least one of the one-side limits does not exist. Okay, so both non-removable, jump or infinite, removable is your point, or in other words, a hole. Okay with that stuff? Okay. At the bottom, find the points, intervals is what we're really going to be looking, at which the function is continuous. And read that as we're going to find all intervals where the function is continuous. There's a homework question that reads really weirdly, I thought, when I was working on the homework this morning. But basically, they're looking for all intervals at which the function is continuous. And then we're going to talk the points at which the function is discontinuous. So, what's the first interval that this function is continuous? If we start on the left, it's continuous from where to where? What is it? There's no arrow there, so don't use negative infinity. She's tricky like that. If there's an arrow, I'd go with negative infinity. So when we do intervals, it's always in terms of x values. So the first one goes from here, which is the x value of -5, to where? Where's our first spot that we have a break and we're not continuous? -3. So the first one we're going to go with is -5
Is this with the brackets?
to -3.
Like where it does touch, or is that a different thing?
I have them all with parentheses here. I was just trying to reason that out, make sure that's right. The continuity intervals you usually don't have the equal to. I'm trying to think if you ever would. That's where I'm not sure. I don't think you would. I think it's just the interval.
Okay.
Okay. -5 to -3. What's the next continuous interval? -3 to what?
2.5.
That'd just be 3.
That's a tough one. Okay, so -3. Does it keep going through here? I would say yes, because that is a filled-in dot. Yes, it's where two graphs connect, but it keeps going, doesn't it? Now, my brain is saying 3, because what is it looking like there is here? An asymptote. Now, why are some of you hesitating and not saying 3? There's no arrow. However, I went to 3, which means she went to 3. So we're going to go with there really is more of an arrow there. Okay, so -3 to 3, which means assume there's an arrow on this side as well. So what's my next interval? Three to 5, so 3 to that next hole. Then where? 5 to 7. Then where? I think she did 7 to 10. That's kind of, it's not very consistent, is it? I feel like I need to adjust one way or the other next time I teach this. I feel like they either need to all be arrows or all need points, because she treated these as points, but she treated those as arrows. So I'm seeing the disconnect here. Again, it didn't process that way when I was doing this on my own, but standing in front of you guys, I'm processing with you. So, yeah. Okay. Just in general, or do you have a more specific? Just in general. Okay, so we're talking about where is this? We're looking at continuous right here, right? So basically we're going from hole to hole or hole to asymptote, or, you know, basically where can I trace the graph? So like right here. My graph starts here, and I can trace this graph from here to here. This is at the x value of -5. This is at the x value of -3. So my graph was continuous from -5 to -3. That was my first interval. Then I had to stop here at -3 because I can't just keep drawing. I have to pick up the pencil. It's no longer continuous. And it's continuous because of this hole right here. So my next interval still starts at -3. But as I'm going, this dot is filled in so I can keep going. And I'm going all the way up here. So this interval, I started at -3. But then the x value that I stopped at is, we're going to imagine that there is a asymptote there. And so when you talk about that asymptote, we always think, okay, it's getting closer and closer to 3, not touching it. So that's a 3. Then we hop over the asymptote. This side of the asymptote is also considered 3. And how far until I have to take a stop? And I go 3 to the x value of 5. And there's a hole. So I had to take a stop. So that's 3 to 5. You're clicking now? Okay. So 5 to 7, 7 to 10. I got the impression I should just, okay. Now, the other part of this question was the points at which the function is discontinuous. So I'm going to list these as my discontinuities. You have a section like this in homework. So discontinuities. You're going to give me a point that is discontinuous. I want to know, what is it? Is it a hole? Is it an asymptote? Is it removable? Non-removable? Point discontinuity? Jump discontinuity? Infinite discontinuity? Whatever information you can share. So, give me a point to start. Okay, so I'm just going to list it as the x value. So Maddie is saying there is a discontinuity at x equals -3. Agree?
Yeah.
What is it? It's a hole. And if it's a hole, what do we know about it? It's removable. I don't know why I didn't write it down. We could also call it a point to discontinuity. I don't have that written down for some reason, but yeah, I agree. I don't want to write the word. Well, I probably should. Okay. What's another one? Okay. X equals 3. What do we know about x equals 3? Okay, it's a vertical asymptote. And what do we know about vertical asymptotes? Non-removable. And we can also call them what? I don't know if anyone said it, but I wrote it. Infinite discontinuity?
We can do it right all three things.
It's more just understanding all the terminology. I don't know. Mine's kind of hit and miss here. It's just knowing, understanding all the different terminology, basically from the top of the page, which the top of the page never really called them bird asymptotes. That was me. But just knowing the vocabulary. What's another one? Okay. X equals 5, and what is 5? Okay. That's another whole. So similar to -3, right? A whole is removable, and it's called a point discontinuity. What else? X equals 7. What do we have happening at 7? Okay. That is a jump discontinuity. Not something we talked about really in pre-calc, is it? Removable or non-removable? And that's what I stress, because I have to stop and think about that one too, because I'm so used to teaching pre-calc, and we don't talk about what kind of a jump discontinuity. Okay. I don't think I'm gonna write this one down. I'm just gonna kind of mention it. She mentioned -1, and her reasoning is that, so this is a piecewise function, and we haven't done a lot with piecewise functions. I wish I could take you guys back to Algebra 2, because I've been teaching piecewise functions in there. But the idea with a piecewise function, and I don't know if it can't be defined both, but this dot, I think generally how piecewise functions work is this point is either defined with the left side or the right side, but it's not defined both places. And so she argued that there would be a hole there on one of the pieces. My argument would be that it's not a hole, though, because it does exist on one graph or the other. So just kind of throwing that out there, but I wouldn't say there's a hole there because the graphs meet there. It's connected. So, okay. What's on my next page? Okay. This next page, I mean, it's basically just a lot of the information, okay? The top, just one side continuity. It's called left continuous if it's only continuous from the left and equals the value at the limit, okay? It's called right continuous if it's only continuous on the right and equaling the value. So kind of like what happened at the 9 on the screen earlier, it was left continuous because it just didn't exist from the right. Continuity, we've already talked about that, right? F of x is defined on open interval. F is continuous if the limit is equal to the point. We'll talk some about upcoming continuity on open interval versus closed interval. It's continuous on open interval, so with parentheses, if it's continuous at each point. Closed interval, it's basically the open interval, and it has to include the left and right pieces. There's some continuity laws of basic functions. These are more pieces that will come up as we go. I don't know if there's anything that stands out there. They'll come up as we talk about them. And then there's some properties of continuity. The fact that, you can multiply by something. You can add and subtract. You can multiply. You can divide. So these are all pieces that we will talk about more and work with more as we continue talking about limits. And I might as well stop there, right? So, remind me tomorrow, we're going to talk about number 3.